So next up we have Rodrigo Ferreira. He's an automation engineer working on the interlocks controls and monitoring section of the vacuum group at CERN, where he's responsible for the PLC software development and field buses. And he's about to tell us about how the integration of wireless communications in the vacuum control systems.
All right, thank you very much for the introduction, and good afternoon, everyone. Before we dive into wonders of wireless, it's maybe better if I give you some context. So why we are doing what we do, and what's the reason behind changing from how we do it now. So here's something that you might know. This is our lovely CERN Accelerator Complex. So not only we have our flagship LHC here, but we have a full chain of particle accelerators which work as an injector chain. And all of these accelerators, in one way or another, they require vacuum. So we need vacuum for the insulation of the superconductive magnets, which are cryogenically cooled. We need also high vacuum for the insulation of the cryogenic transfer lines, which transfer the liquid helium down to the tunnels to supercool the magnets. And most importantly, we need vacuum for the beam pipes. In the beam pipes, we have ultra-high vacuum because we cannot have the particle beam interacting with any stray molecule which actually might be in the beam pipe. And contributing to this vacuum, so this vacuum is partially created and maintained using two mobile devices. The first one is a turbomolecular pumping group. So this is essentially a mobile trolley with a primary pump and a turbomolecular pump and a set of accessory valves. This is currently controlled with the Step 7 200 PLC, but we are upgrading it now for Step 7 1200. And we have our bakeout racks, because certain elements of a vacuum system need to be baked if we want to attain ultra-high vacuum. These guys are controlled by a Step 7 300, and all in all, we have around 400 turbomolecular pumping groups and 200 bakeout racks. During technical stops, and only during technical stops because they cannot be in the tunnel during operation due to radiation. So during these technical stops, the operators move these two devices next to the tunnels, and using their touch panel, they specify their location. So for the case of the pumping groups, it's the flange that they connect it to. For the case of the bakeout racks, it's the sector they connected it in. And obviously, if we have them on the plant, if we have them working, we want to integrate them in our control system. And right now, this is done using Profibus. So all around the LHC, we have several Profibus networks with several masters, working as a master for the network. And these cables have open connectors to which the operator is going to connect our mobile device. There we go. So during technical stops, these devices are installed and integrated into our vacuum control system. But due to the way that we do this with wired Profibus networks, there are some issues that come by, and sometimes that hamper operation. The first one is that the guys who are actually in the tunnel installing these devices are not control experts and are not field bus experts. So quite often they create a wrong topology, they forget a shunt, they forget a termination resistance. And if you do this, you often bring the whole network down. So you affect not only your device, but all the devices in this network. Secondly, is that the constant manipulation of cables and connectors, as you, for example, see here, it degrades the material early. So this is not supposed to be connected and disconnected hundreds of times in 1 year. Then we have the issue of address conflicts. So in Profibus, we have 124 available addresses. And if you have 600 devices, you can see how this might be an issue. So sometimes we end up with address conflicts. And finally, we only have cabled Profibus networks in the LHC, in the LINAC 4, and a couple of new experiments. And it's very expensive to cable other 20 or 30 kilometers of tunnels. So the answer to all our issues is obviously wireless, which is the actual purpose of this paper and this project. So maybe the initial idea would be to use the standard Wi-Fi, the 802.11. However, we cannot do this because usually for long shutdowns, for a 1 or 2 year shutdown, we usually have wireless access points in the tunnel. This is not the case for shutdowns of a few hours or a few days. What we do have, luckily, is a GSM network in all the tunnels. So this is done. They keep the radiation-sensitive material in shielded areas, and they use a leaky feeder antenna. So essentially a radiating cable that goes all around the tunnel. And we have this in all the accelerators and experiments at CERN. Now this work, this network, it's provided by Swisscom. So it's a Swiss telecommunication operator, but it's managed by CERN, which is a good thing because the APN, this is the gateway to access the data network, is actually managed by CERN, and this is going to be a very important detail later on. So this means that we have in all accelerators a GSM network. We have 3G in all areas and LTE in almost all of them. So now that we decided to actually use GSM for our wireless system, we have to provide GSM connectivity for our PLCs. If you're using a Step 7 1200, you can do this natively. So Siemens has modules which provide native connectivity for GSM. But this is not the case for the Step 7 300. So for Step 7 300, as it's an older ecosystem, we're going to have to use the Ethernet port. And because we want to use the same solution for the pumping groups and the bakeout racks, what we decided was to use this Scalance router. So this is a small industrial router. And essentially, it's got a 3G modem. You just put an antenna here, you pop in a SIM card, and then you have a 2-port switch for your internal network. Now, there is a cost associated to these SIM cards, even though the APN is managed by CERN. We are billed 10 Swiss francs per month per SIM card, and this somehow conditioned our implementation of the thing. Because otherwise, we could just stick one of these in each one of our 600 mobile devices, but it would be hard for me to justify my boss that I need 6,000 Swiss francs per month just to run this system. So what we decided to do is we keep a stock of these 3G routers. Imagine we have 20 or 30. Because even though we have a lot of mobile devices, rarely there are more than a few dozen in simultaneous operation. So we keep this in stock, 20, 30 of these, each one with its SIM card. And then whenever intervention is required, we just connect it to our mobile device, our bakeout rack, our pumping group, and we ship it down to the tunnel. And with this, we end up with a network topology, which is something like this. Here's our bakeout rack. Here's our mobile pumping group. And right now, each one of these mobile devices has been equipped with its own 3G Scalance router. So these guys are given fixed IPs in their local LAN. And these two, here's our lovely Swisscom network. And for these ones, we pop in a SIM card. And these SIM cards are pre-registered in the network. And they are attributed by the network fixed IPs. And these fixed IPs, because the APN is managed by CERN, there we go, we can route them directly through the CERN technical network. So this is the network that has all the controls equipment. This is air-gapped from the general purpose network, as it should be for any connected control system. And what happens is that we can now address these IPs here of the SIM card directly through the technical network without going through the internet, so without ever leaving CERN infrastructure. And this is very important because essentially the security of our control system relies mostly on this. But it doesn't matter that we can address our routers here if we cannot actually route the traffic to the PLCs, which is what we need. So here's a summary of what I just said. Fixed IP on our technical network, local network here for the PLC, and we need to reach this PLC. And what we do for incoming traffic is we route 2 particular ports to the PLC. So port 102, which is the port used by a Siemens Step 7 communication, is routed to the IP of the PLC. And this means that with the IP of the SIM card that we have here, we can actually connect directly to the PLC. We can make a SCADA connection. We can make a connection for programming or diagnostics. And also we route port 2424. This is a port that we chose, which is where we implemented our own mobile communication protocol for the integration of these devices into the control system. So for this PLC is reachable on the ports we need using the IP of the SIM card. Regarding outgoing traffic, okay, we just use network address translation. This is it's a standard practice in networking. Essentially, the router changes the headers on outgoing packets to make it seem like they came from the router. And then when they go back in, the reverse process is done. For this, I invite you to take a look at the paper. This is a little bit explained there. So with this network structure and network configuration, we can access our slave PLCs here through our SIM card, and we can do it the same way, regardless if it's a bakeout rack with a Step 7 300 or a mobile pumping group with a Step 7 1200. So now that we have this, we can actually start looking into the implementation of our mobile protocol. And this is the part of our system that is actually going to integrate our devices in our SCADA. So one thing we wanted to avoid was to having to configure 50 or 100 new connections in the SCADA, because we're not quite sure how the SCADA would deal with this. So here's a bunch of bakeout racks, here's a bunch of pumping groups, and this is the master communication PLC. So what we did here, here's our SCADA server. We run a WinCC control system, SCADA, sorry. So the way we did this is that all of the slave devices speak only to our master communication PLC. So there is no direct communication between the slaves and the SCADA server. And the SCADA server is only connected to the master PLC. So this means that we have a system that is centrally managed by one or more than one master communication PLC. Actual communication between each one of the slaves and the master is implemented using open user communication. This is a set of functions that Siemens provides that allows you to, essentially it allows you for your PLC to speak to any device that supports Ethernet, that has a TCP/IP or UDP protocol implemented. So we can establish IP connections between our PLC and any other thing. Here we are establishing an IP connection between two PLCs, so each one of our slaves and our big master communication thingy. And okay, you can configure this to run TCP, to run UDP, or to run ISO. But more importantly, all connections are configured and managed during runtime. So if you work within the Siemens ecosystem, and if you want to, you know that if you want to configure a Step 7 connection, you have to do it previously in the hardware configuration, which would be a bit of a mess for us. Here I have extra microphones. So with this, it's much better because every time we add a new SIM card or a new mobile device which needs to be connected, we simply do it in code. So we don't need to reprogram anything. We just add a new block with this IP, which is really a blessing for our case. Usual stuff, connect, disconnect blocks. You send and you receive data with T-receive and T-send blocks. And what these PLCs exchange in between them, it's they exchange 138-byte packets. In our PDU, for our specific case, our 10 bytes are control data, and then our actual data comes here in these remaining 128 bytes. We don't have that much time, and this might be a bit dense, so I'm going to go over this quite fast. You can look at the paper if you need a bit more details. So master and slave are exchanging these packets in a request-response way. You have a type ID, which identifies your device, if it's your master PLC, if it's a given model of a bake-out rack or a pumping group. You have a couple of headers for a connection ID, which is user handshake and etc. Let's go forward a little bit. And then your request and response codes are what actually identify what's going on in the particular packet. So from the master to the slave, it can send a handshake. It can request the device name. It can request the device position and occurrence number. So this is all data that the operator input in the touch panel when he installed the device in place. And the slave, so the mobile device, responds in the same fashion, more or less. And as most protocol communications are, the whole thing is managed by a couple of state machines. Software architecture, so just going quite fast over this, everything is implemented with function blocks. So we have one function block for the master, which we instantiate once for each slave device, and then we have one function block on the slave device with a single instance that identifies this particular device. And regarding the state machines, we have one main state machine running on the master, and then one on the slave. One instance per slave device. And this is not supposed to be an in-depth representation of the thing. It's just to give you an idea of how the automatic registration procedure works. So the master, whenever he checks that the communication is up, it sends a handshake to one of the mobile devices, and the mobile device responds with the correct handshake. And then this whole procedure of requesting the name, of requesting the position, and the occurrence happens. Once everything is done, if everything worked on correctly, the device appears now registered on the SCADA, exactly in the synoptic where it should appear, and the cyclic data exchange commences. So the master continuously requests the state and sends commands to each one of the devices. Now, does this work? Yes, it does, and I can prove it. So we sent it down to the tunnel. We mounted this control crate into a small mobile trolley, along with the UPS and one of these Calance routers. And then we connected to the network. We had the master in our lab and the technical network, and we moved it for around 1 kilometer, and we tested for around 1 hour. And if anything, the connection is more stable than what we have on the surface. So for 1 hour, there were no connection breaks. The data exchange continues correctly. So it worked even better than we expected, and better than it does on the surface. So just to finalize now we're just finishing up with development of the SCADA the SCADA functions, and we're going to deploy this later this year or early next year. So all the issues that I told you about in the beginning of the paper were addressed with this mobile system. So the SCADA integration is now possible in every accelerator without the need for us to install further infrastructure. There's no cable manipulation, so the operator will not mess anything up, if you will. It will not break the network by making a wrong connection. And there will be no degradation of material because there's no material to degrade. Our address space has increased. Okay, it depends on the subnet you are using, but we are no longer limited to the 124 Profibus addresses. And finally, IPs are automatically attributed, so there will be no address conflicts. That's all I have to tell you. I don't think we have time for...
Yep, let's thank the speaker. So we'll open it up to the floor for some questions. One over here.
What about the communication speed? Is it much faster than the original Profibus solution?
It doesn't make much difference because what we are exchanging is the state of a pumping group. I think it's 48 bytes, which we exchange every 2 seconds.
But if you plan in future to be connected directly to the SCADA,
it would be faster. Yeah, for sure, because the networks we have in the tunnel. So in the LHC, you have 8 main access points where we have our PLCs, and then in between the 8 access points, we have smaller alcoves. So these Profibus networks, from the PLC to the actual tunnel, they go quite a long way. So we end up configuring them for a low speed just for extra stability. We haven't tested the exact throughput of the network, but it will be for sure faster than the Profibus. I think there was one there.
Mark.
Hello. You said that Swisscom were providing the GSM network into the tunnel, and that's connected onto your technical network. Presumably, there's other services coming over the GSM. So how are you managing the security in that, that Swisscom are managing this configuration, and through a, shall we say, a misconfiguration of their setup, there could be a hole into your technical network?
Okay, this is entirely out of my scope because it's such a big institute that everything is handled by the specific section. To what I was given, the information I was given is that Swisscom does provide the infrastructure and the basic for the GSM network, but then the APN, so the gateway that you actually use to tap into a technical network, is managed by CERN. I'm sure there will be someone here from CERN that will be able to tell you better about this. At least I know that Stefan Luders is here, and he's the main boss of the security. So
yes, I know Stefan. Thank you.
Well, I could do mine as I have the micro. I have one question regarding all this system. You are just monitoring the bakeouts, or you are also implementing logics in the master? Let's say you are controlling the bakeout from the master in case of there's a problem with the heater?
The masters are completely, the bakeout process is completely controlled by the rack I showed you before. So to the rack you connect your heaters, your thermocouples, and you have some PIDs that actually regulate the ramps you need. What you do remotely right now, you can only monitor the bakeout racks. So with the Profibus system, you cannot send commands. With this new wireless system, you can do the full control. So the control is still done with the rack, but you can turn it on and off. You can set your set points. You can restart your process. Sure.
One more quick one.
I have a question regarding incident management. I mean, sorry, here.
Yeah.
Yeah. Now Swisscom is part of your technical chain in the control system. So when Swisscom fails, how do you manage? Do you have any service level agreement with Swisscom? On how do you manage failure from Swisscom?
Again, this is beyond my scope, but the main thing I would say here is that failure here is not catastrophic. So if you lose remote monitoring, okay, you lose logging for that period, but the process will continue because everything is managed by the device themselves and not by the master. I'm sure there is some specific agreement between CERN and Swisscom regarding uptimes, but I don't know how this is managed.
Okay, let's thank the speaker again.